Okay, so let me just go ahead and, this is where we left off last time. Let me just go ahead and run this real quick so we can see the evidence for the question we're talking about. Then I'll let you tell me how it works. So we have our main procedure. So all programs begin and end with main. So we happen to call this guy main just to be consistent with that. And the very first thing we do is we call a procedure called AddNumbs, which is down here. So this changes control. Now, some of you had referenced last class about these jump commands. All right, so what a call command does is it is a jump with a jump back built into it, right, upon returning. So when I say call AddNumbs, it jumps me to the AddNumbs label in our code, so later on in the code. Actually, it doesn't even have to be later on, but it jumps us to that place in our code. This guy is a procedure. Some procedures play by certain rules. All right? And in here, we do a couple of things, adding, blah, blah, blah. And ultimately, we hit return. But what we want to do is we want to watch what happens to the stack on this call right here. All right, so we'll go ahead and emulate this. Scoot this over. Let's get our stack up. So right now, the stack is not being used. This is just the arbitrary top of the stack. So we'll go ahead and step over AddNumbs and notice that's the top of our stack. Put a 3 there. Okay. Then we go ahead and we do our couple of add things. We move it at 15 into AX, then we add 21 to that, giving us our answer, also stored in AX. So there's our F in AX, which is 15 in hex. Then there is our result of AX, 15 plus 21 is 24 hex. So 15 plus 21 decimal is equal to 24 hex. Then we hit return. So notice the top of the stack is still 3. When I hit return, that pops off the stack, and we're back to the line immediately following the call to AddNumbs. Tell me what the meaning of that 3 was. No, not really a memory address. It involves memory, but pretty much everything in assembly does.
It's the pointer to the next line after the procedure call in memory for the
program. Okay. Tell me about that.
So
obviously it got us back there, right? One way or another. But what's the meaning of it? How was 3 actually used?
3 lines from the main proc, that's 1, call AddNumbs, 2, push AX, that's 3.
Okay. Pretty close. Close.
Unless I nailed it.
You're gonna say you know.
I think I nailed it.
I think I got that right. All right, so we've had several examples in here up to this point about base addresses and offsets off of base addresses, right? Make sense? So when I say something is an offset off a base address, what am I talking about? What does that phrase mean to you? We've seen several examples where we store the base address of something and then we walk through memory from that base address some number of elements. We looked at arrays. That's how arrays are built, right? Okay, so when we look at an offset, we go to a base address. If it's an offset of, in this case, 3, we walk 3 elements off that base address. Okay, 3 times the size of an instruction. Okay, whatever that is. So in 8086, an instruction is it's kind of a 48-bit thing, but forget about that. It's not really important for us. But in your reading and in your last homework assignment, they had you talk about converting a MIPS instruction into its binary equivalent. Remember that guy? So that binary space that is, here's the magic trick number, here's the parameter, here's this parameter, that is the size of an instruction, right? Whatever that size is. Not really important for the theory here. So I'm walking an offset of 3 from the base address, whatever that base address is, to the next line. Okay, so we're right in saying the number that was pushed onto the the stack is related to the next line of code that we should return to at the completion of this procedure. All right. So that 3 is off the base address of what? What's the starting point for our? Yeah, the dot code, which is the code segment of an 8086 program. This is where our code segment begins. All right, so this is the base address of the code related to our assembly program that's currently working. So a offset of 0 would be base address of this plus 0 times size of instruction, which would keep us right here. This is an offset of 1. This is an offset of 2. This is an offset of 3.
So is this all contiguous memory then? This entire program is like stored in exactly this?
Yeah.
Yeah.
Mm-hmm.
Okay.
Because it has to, otherwise we'd be jumping to get to instructions, we'd be jumping from place to place to place to place all throughout memory.
Yeah, I figured it would return to the program that called it, or the procedure that called it. So like if there was a third one that was like subnums, and that was inside of AddNumbs, then I would think it would jump back to the AddNumbs, but it would actually just do the offset from the dot code. Correct?
In this case, that's right. When you start having multiple assembly code files that you then link together,
Sure.
what it does is it effectively creates a giant assembly language program, and it does all the offsets for you. So the idea of, I think at some point you in your reading it talked about linking assembly language programs. Was that somewhere in the reading? You don't remember that? Okay. Well, so the idea is we first assemble it, and assembling it converts from humanish looking assembly language in whatever, whether it's 8086 assembly or MIPS assembly, doesn't matter. It converts from that human looking thing into zeros and ones. The equivalent for that architecture. So MIPS, it would be the zeros and ones for the instruction for MIPS. Here would be the zeros and ones for the 8086 instruction for Intel architecture. Now, that's the assembling part of it. So we can assemble a whole bunch of assembly language programs and convert them into the even lower, the machine language for it. Well, if you have a whole bunch of assembly programs that are related or reliant on each other to accomplish a task, what we then do is we then link them. And what that does is it puts them all into a giant executable file or a .com file, depending on the model we use here. So model com is a .exe, model tiny is a .com in the Intel architecture. But regardless, it turns it into an executable file that you can just double click on and it runs. Or in Linux, you / and run it. And what that does is it takes all of your bytecode, all of the machine language that was generated from assembling it, and puts it inside of a file next to each other and updates all the offsets. These are line numbers, if you will. This is line 1, 2, 3, 4, whatever, so it's contiguous. And then make sure the offsets, all the math works for where stuff is relative to where other stuff is. So linking is mostly an automatic organization task. Does that make sense? Just putting everything together in a single file so that you could double click on it and it works. Or doesn't work if you wrote bad logic or something like that. But that's how we ultimately get to run it. All right, so having said that, last time our idea was, because remember though, the whole premise here is, we have a limited number of registers. Therefore, if we're going to rely on our registers for holding our values, our parameters into a function, we are limiting ourselves in a couple different ways. A, we're limiting ourselves for the maximum number of parameters we'd have. Now, we're always going to be limited to some number of some maximum, because our stack cannot hold an infinite number of things. All right, but if we utilize the stack, we've certainly increased the maximum number of elements that we can store in or maximum number of parameters that we could pass to a procedure. We are also, if we can use the stack, keeping us from having to store, preserve all of the current values of our registers. Now, I mentioned last time that in some of the newer architectures, the 286 Intel architecture and newer, there's some catch-all commands that allow you to do a single command that just pushes all of the registers to the stack, and then that same command that restores all the registers from the stack. Okay, but we do need to be careful about any state changes in the stack that might occur between those two calls. And we're going to be looking at that a little bit today, so I might throw a little hint in there for kind of what we're going to talk about next. All right, so we saw last time that we ran into a problem. What we really wanted to do, let's kill this here, is we wanted to have a procedure called AddNumbs that took the two top elements of the stack and added them together, storing the result back at the top of the stack, right? So that whoever we returned, we'd be able to look at the top of the stack and get that value back. All right, that's our answer, stored on the stack, which then means that we don't have to worry about overwriting registers or something like that, or overwriting very many registers. You know, we're using AX here as an accumulator to do our math because that's how add works. We could have used a variable if we wanted to, and we'll talk more about variables today. But generally speaking, if we can minimize the amount of overhead, the amount of organization we have to do related to our registers, we're probably better off because these guys are kind of important and they're precious resources. So what we wanted to do last time is something like this. We might want to do a push 15, push 21. So get the two numbers we want to add together onto our stack, right? So we're pushing these two immediate values onto the stack. Then we're calling AddNumbs. And then what we would do is inside of AddNumbs, we would pop into AX, which would bring our 21 into EX, or well, in our mind, it would bring the 21 into AX, which should be at the top of the stack, although it's not at the top of the stack because a new dude got thrown at the top of the stack. Then we would pop into BX, for example, load up a couple of registers, then add AX, BX, and then push AX, which would put the result back onto the top of the stack. So grab the two top elements from our stack into registers, which would then remove them from the stack. Do some math with those guys, okay? Then push the result of that math, because in x80 or in 8086 assembly, the add instruction has a destination and a source, and the destination is where the result is. So this says add AX plus BX, storing the results back in AX, as opposed to MIPS, which actually uses 3 registers. It has where am I storing my answer and what am I adding is the other 2. Both of them are valid. It's just kind of showing you little nuances between languages. At the end of the day, it kind of does the same thing. But if we think about it from an Intel architecture perspective, the less registers you have to work with in a particular call, maybe the better. The less stuff you have to worry about overwriting. So rather than having 3 registers involved in this, I could do the math in 2, which we might say more times than not might be beneficial for us, but every now and then we might want to not lose what was in AX. So then you have to preserve what was in AX, right? Maybe push it onto the stack. That way you can do the math. You know, move whatever's on the top of the stack into another register and bring AX back to what it used to be if you need to preserve it. So the stack becomes this kind of go-to tool for temporarily throwing something somewhere while we do something else, only to bring it back later. But at all points in time, we have to keep track of what is the current state of that stack. And as we saw last time, that call instruction manipulates the stack. And we have to be aware of that. All right? So we'll pop into AX, the top of the stack, pop into BX, the top of the stack, add AX to BX, storing the result back in AX. All right? Then we'll push AX onto the top of the stack. All right, so let's watch what happens there. This is kind of what we did last class, and we saw this was a problem. All right? And then what we want to do after AddNumbs here is we can go ahead and do pop into AX or something like that. That should put our answer in AX in our mind. Okay? So we'll go ahead and run this. take a look at the stack. We'll go ahead and do our initial, well, here we're pushing 2 values onto the stack. So there's our, this is 15, this is 21. We kind of picked bad examples last time, that's why we got a little confused, but that's what those are, okay? Then we're gonna go ahead and call AddNumbs, which we know has a side effect. And we got a 7, right? Why did we get a 7? We used to have a 3, now we have a 7. It is further down, but is it further enough down? These are the same 2 numbers we had last time, right? 7 and 3, because I think we wrote pretty much the same code. So we'll play it out. We'll see where it comes back. So this 7 is now at the top of my stack. Okay. Next guy is my 21. Next guy is my 15. We're converting it decimal. All right. So we'll go ahead and pop into AX, top of the stack, which gives us our 7, not what we wanted. Then we'll pop into BX, the top of the stack, which gives us our 21, 15 in hex. Then we want to add those guys together, storing the result in AX. There's our 1C, and then we'll push 1C back onto the top of the stack. So that's our top of the stack right now. Then when we hit return, nothing happens, because this return statement looks at the top of the stack to bring us back, to get us back where we came from. And it had remembered a 7, yet we have a 1C in there. So when we hit that, there's no ops there, and because it's looking at 1C as the next instruction pointer, and it doesn't get us anywhere. All right, so let's stop this for a second. So before we investigate that 7, how can we fix this? How can we make, I still want to use the stack for my parameters, but how can we make this return statement bring us back to the right place? Do what with it?
You gotta move it, so since it moves, can you move it back?
Okay. How do you want to move it back?
I don't know, like add 1 to the stack pointer.
Oh. You want to manipulate what the top of the stack is.
Yes, that's right.
Okay. I think the stack pointer is going to be read-only for us. It's possible we can do that.
It kind of worked when I was messing with it.
Okay.
I got it to at least drop. I could not get it to go.
I get it.
up in the stack.
I get it. So you want to change the offset of where the top of the stack is.
Yeah.
All right. What's a cleaner way of accomplishing the same thing?
Can you just put it in a register?
Preserve it, right? So I could come in here and I could say, look, I know that the top of the stack right now is an address I don't want to lose. It's an offset that I don't want to lose. I'm going to go ahead and throw it in CX. You can throw it in a variable. You know, we're going to talk about variables. Right now we have registers to work with. So I'll go ahead and pop the top of the stack into CX so I have it. Then I can pop into AXBX. Now I'm doing the correct math, correct? Then I'm going to push my answer back onto the top of the stack. And then ultimately I'm going to push CX back onto the stack, returning the top of the stack to be the place I want to return to. So I've temporarily removed that bounce back address, that offset, into a variable, did all the stuff I was going to do, changed, put the stuff back on the stack, and then right before I call return, I throw the answer, the return address, return offset, I put that back onto the top of the stack so the return statement can get us back. That makes sense? All right, so we'll go ahead and run this. Show our stack here. So there's our push 15, push 21, call AddNumbs. So there's our 7 at the top, and then the 15. Well, so this is the 21, this is the 15. Then we'll pop into CX. This should give us the 7. There's our 7 in CX. We preserved it. Then I'll pop into AX, pop into BX. There's our two numbers we want to add together. We'll add those two numbers together, storing the result back in AX. So there's AX is 24. Then we'll push AX back onto the top of the stack. So there's my 24 at the top of the stack. Then I'll push CX, which was my preserved return offset, back onto the top of the stack. There's my 7. Now when I hit return, it brings me back where I was supposed to go. Make sense? And then if I want to pop into AX, which actually already has our answer in it, we'll overwrite a 24 with a 24. So there's that, because we happen to do the math in AX. We're good to go. Let's forget about the fact that it just continued on here. That's evidence of linear. The instructions are in a row, because now we've just run into the address space of our AddNumbs. Does that make sense? Even though I called it here, I ran off the end of main here, and now I just keep trucking. So if I want to get past this, I would have to jump to a label like end of program or something like that, right? Okay, so given this, what does that 7 mean? Let's just reload this. Step, step, step. There's our 7. So this is telling us how to get back. We see that's the evidence of it, right? We see that 7 gets us to this line right here. Does it not? 0, 1, 2, 3, 4, 5. What do you think? Clearly, it does what we've said it does, right? It gets us back. But it has to get us, I mean, that has to be meaningful values, right? It wasn't just a made-up number. The 3 and the 7, they're kind of consistent, right?
I don't know why, but does it go from .data instead?
Okay.
But then the
So-
3 would have run.
I know, but I don't know why, but in this case, maybe.
All right. So reasonable suggestion, right? If we had done the 7 first and saw that, we might have drawn that conclusion.
Yeah.
We might have said, oh, okay, well, this is 0, 1, 2, 3, 4, 5, 6, 7. Oh, that works. But then when we do the 3 and we saw that it was 0, 1, 2, 3 when we had our call as our very first line here, that wouldn't have taken us to the right place, because this would have been 0, 1, 2, 3. That would have been the offset.
Well, that would have been the offset, but the mainage would have went right into it.
Are we doing anything different from when we did the 3? We didn't have those push statements in there. did
That's
we?
true. We didn't have the push statements piece, so that means the call was up higher.
Yeah, I was just thinking, because if we were storing variables or something, then it would start from the .data instead of the .code.
Oh, I see what you're saying. That the offset would be
Something-
based off of something you used. Like if we had the data section, we had variables in there, then all of a sudden that is incorporated into our program and our offset starts. Yeah, in this case, we didn't change anything up there. Let's go ahead and run this again. Let's look at our instruction pointer here. All right, so our instruction pointer is currently a 0. When I take a single step, that guy jumped to a 2. Run it again. Instruction pointer is 0. We're sitting at this line right here. I step over it, now it's a 2. I step over it again, now it's a 4. I step over it again, now my instruction pointer is an 8. So this was, when I passed this was a 2, this was a 4, this was an 8 down here. What does that tell us about what's the instruction pointer? Trying to fill in the gaps here on what all these other guys are doing for us.
Okay, so instructions aren't necessarily one byte or whatever that is, I guess I would say. So the push instruction is 2, so it takes up 2 spaces. So when you say I need to go to the second push there, you go to 2, not 1, because it's push 15 takes up 2.
Well, I think what it is the first instruction pointer, it takes you to the main. In the main, it doesn't do anything, so it goes to the next line.
Well, to circumvent this a little bit, let me just hit next a couple times on these pops. We're currently sitting at 8, right? Now we're at 9. Now we're at 10.
What? Oh, yeah.
Now we're at 11.
Wait, do it one more time.
You want to start over?
No. Wait, what did it go? What was it at? And then it went to? It went from
This
9
was
to 11, right?
No, 9, 10, 11.
9, 10, 11. These were all ones. 1, 1, 1.
And now the next one should be 2.
Okay.
No, 3.
You take a 3?
Wait. Yeah, sure. 3. Times 2. I'm still sticking with my answer. It's the amount of like memory and stuff.
No, the correct thing for you to say, I'm still sticking with my answer that I nailed it. Or I'm here, so I nailed it. All right, so we're back at the beginning here. We're focused on the instruction pointer. Right now, the instruction pointer is 0. I have not executed an instruction, right? And I start at main, like I've advertised. All programs begin and end with main. I go ahead and I take a single step, and we're at 2. Now, that means that this push jumped us by 2. This push jumped us by 2. Call AddNumbs. This goes to what? Up to 8. So that jumps us by 4. Pops. 1, 1, 1. Then our add jumped by 2. What did push jump by before? 2. So we would expect D to be F. How many did that jump by? What's the instruction pointer? What's the purpose of the instruction pointer?
Went to the start of an instruction.
Okay. The address of our next instruction, right? It should point to the next instruction. So it's saying that the next instruction, this guy right here, is FE. What number is FE? What's the decimal value FE? So that's 14 plus 16 times 15? 16 times 15. That's the, so this is the F is value 15, and it's in the 16th place, and we add to that an E, which is 1 times 14. So that's 254. All right. So this number is 254. What does 254 mean in this stuff over here? How did our instruction pointer all of a sudden just fly down to that value? Is it a mistake? Or do you suspect when we do this again, it'll do the exact same thing? Do the same thing? Okay. It's an EMU 8086 bug. So it's like, no way it should just be jumping that far. Are any of these other guys switching up? These start off at 700. These guys are all zeros. This guy is a 100, 710. All right, so let's take one step. What is this guy? Instruction pointer went here. stack pointer. Okay, so SP is our stack pointer, and here's our stack pointer, bucket FE, so that keeps track at the top of the stack. All right, so stack pointer currently points to where the top of the stack is. All right, so that guy changed. Anything else change? These guys stayed the same. These guys stayed the same. Did SS change? Did CS change?
No, the blue means it's in hex.
Well, every time it's changed.
It's blue. It's blue. Yeah.
Oh.
Okay. So only those two guys are changing. What about our flags? Let's take a peek. Let's take a peek at those flags. Let's reload here. Take our single step. Flags changing at all? No. They probably, well, they could change after an add, right? Yeah, I mean, I don't think they will in this case. Oh, actually, they do in this case, but for different reasons, not our 0 or our carry flag that we're used to, so don't worry about these for right now. All right, but yeah, so arithmetic instructions can manipulate flags, but had nothing to do with our walking through our code. Okay, so we could take flags out of the equation here. Start right from scratch here. My instruction pointer is currently 0. I'm at the very first instruction that I should run. So very first instruction that's runnable inside my code segment. Now if we're inventing this, if we're writing an assembly language, and we need to keep track of kind of where we left off, where we are, does the code segment sound like a good place to reference from? If you're writing this data segment kind of gets read in ahead of time, right? If you have variables that are defined in the data segment, which we're going to talk about today, those have to be kind of predefined. We're not running our program yet kind of as a startup sequence. We need to run through the data segment and grab any memory that we're requesting and set it aside, right? That's not part of our actually executing the program. That's part of like the prerequisites or the given information for our program. So in our world right now, if we were writing this code segment, it makes sense for us to kind of start there, right? And then we see the very first thing in here is a procedure, and we've kind of noticed that when you have procedures, things just kind of start after the procedure. Now I've said that programs begin and end with main. If I changed the name of this procedure to blah, oh, sorry. I change that to blah. Is that going to make a difference? Yep. So the procedure I'm ending is the procedure blah. All right. Go ahead and emulate that. Start in the exact same place, right? So what does that tell us? That procedures are not executable lines. Instead, they have semantic meaning. They're labels. They're labels that we search for to return to later on if we were to jump to a label. All right, so it didn't matter this guy was called main. We just happened to call it main to make that guy coincide to that statement we've said in languages like Java that all programs begin and end with main. All right. In this world, all programs begin and end in the code segment where our actual instructions start. And we can think of the code segment as a synonym for main in our C-based languages. Fair enough? All right, so our instruction pointer is currently 0. The instruction pointer points to the current first instruction. Okay, we're on instruction 0 right now. It's a 0 index thing that seems to be a consistent thing in computers, right? Things are based on 0. You know, the first thing would be 0, second thing would be 1, third thing would be 2, that kind of stuff. All right, so we're sitting at the very first instruction. And this instruction pointer says to push 15. Step over that. Now the instruction pointer is pointing at 2. So the question is, what does this 2 mean? Now, this 2 here is 2 in decimal, 2 in hex. It's 2, right? Doesn't matter how we want to read it. Small enough number that it's the same value. And this is value 2. we see these lines over here indexed from 0 or from 1 to 8, so on and so forth. This is for human readable, right? We want to be able to, we think we count like that. 1, 2, 3, so on and so forth. Okay, but this guy is 2. What does this 2 mean? Clearly, the instruction pointer is somehow telling us where the next instruction is. What do you think? Now it jumped to 4. This is the next instruction. And then we made a jump to 8. The question is does this instruction pointer have anything to do with what this guy is, or does it have to do with where this guy goes? When I jump from here to here, let's look at any of the other values over here that might change. Stack pointer changed because the top of our stack changed, right? The instruction pointer changed. These guys are the guys that are in blue, changed. So this guy became an 8. What does that 8 mean? We look back at our documentation. We had a good thing on pointers, on the flags, right? I'm sorry, not the flags. This had our instructions, but I think it had the flags before that and the registers before that. Let's do this. 8086. Hopefully this brings up the same document. Is this here's our tutorial thing. Here's our instruction pointer. Instruction pointer register stores the offset address of the next instruction to be executed. Okay, seems to make sense. So it's an offset off some base address. It's in association with the CS register, gives the complete address of the current instruction. Okay, well, let's go and look at what our CS register says in here. CS register is 720. Okay. Whatever that is. Okay, so this is some base address, right? What do you think CS stands for?
Computer science.
Problem solving. This is an address, correct? What might the... We got one good word in there. Code's the good word.
Yes. We're getting somewhere. Code segment. Nailed it.
I've said code segment several times today. I have. When we were looking at this, I kept referring to this as the code segment, the data segment. Okay, so the address of our code segment lives inside of CS. So that's 720, right?
You're reaffirming exactly what I said at the start of this discussion. That it is.
What
So push does not take up 1 space in memory. It takes up 2. So the push instruction is 2 bytes, bits, whatever you want to call it. Two IP numbers. I don't know what you want to call this. So that takes up 2.
The encoded version,
Yes,
the assembled version of push.
Yeah, so push and the variable or whatever. That's what makes up the 2. So you have to jump by 2, and then you do it again because it's push again, and then call, obviously, I guess. Well, call is probably different because if it's going to tell you where the next one is at, then it just...
Oh. So you're saying that even though we've written this in a pretty clean way, just so call AddNumbs, under the hood, some extra stuff's happening?
For sure.
Yeah, there's things that are larger in size than the stuff that's happening right here, right? Okay, well, so let's see if that works out for us. So our base address of our code segment is 720. That's where we live in memory. right? So we are currently sitting at address 720 and we're setting at an offset of that guy at 0. So this line of code right here is address 720. Agree? Seems to make some sense. Now when I jump to here, now remember, we are looking at the human written assembly code, not the actual byte code that's being currently executed. All right? So when I do a single step, it's going to move to my next instruction, which is an offset of 2 from the base address.
In the middle there?
Say this again.
The blue highlighted in the middle box in between that. No,
So
to
if
the
you
left.
click on each,
To
of
the
those,
left. To the left. Yeah, box to the left. That. So the 2 in the yellow, was that the first push command? Now this next
Yeah.
blue.
Yeah, these are the two instructions. Yep. So this was push. That's
Push
the
15.
yep, and there's the 15.
15.
Yep. All right, so that's from your reading when they had you convert the MIPS instructions into their binary equivalent. So this is the 8086 version of that. Okay, so that took up 2 bytes of things. All right, so this is our memory address, 7200. That's an, 720. Actually, this is, I wonder why they wrote it as, this is the number counter from, so just melding them together? Yeah.
Well, that's what it was because that makes sense because didn't it say that you add the IP?
Yeah. But the way they have this written up here is like this is human readable line 0, line 1, line 2, line 3 because the actual address is 720. Just kind of a weird way that they're putting it there. And what are they showing right here? This is what we just looked at in the tutorial. This guy says this is the base address of the code segment. So this is CS, and this is IP, the offset from that. So this is offset 0, offset 1, now we're at offset 2. So when we push again, step over that, we see 6A, same 6A. So 6A must be the hexadecimal magic trick index of push. So if you looked at the instruction set for 8086, 6A must be push. That's the number of that magic trick. Make sense? All right, and what are we pushing? We're pushing a 15. Well, 15 hex, which is 21 decimal. Right, now we get to AddNumbs. And AddNumbs, here's our next 3 instructions. We don't even have to step to see what they are. So we have call, which must be E8, right? And then we have a 0, 1. Then we have a 0, 0. That changed the stuff. But notice that we've now jumped down to 7208. So this was our top instruction. This is our first instruction. Here's our second instruction. Our third instruction, which was the call, this was call, E8. And this was the other 2 things that happen as related to E8. Realistically speaking, AddNumbs is a label that is inside of our that's inside of our program, right? And when we assembled this, that label, this human readable label, likely was assigned kind of an index value, kind of like a Unicode or an ASCII, something like that. You know, so since this was kind of our first label and our second, well, our first label would have been blah, second label would have been AddNumbs. Maybe that's the 0 and the 1 indexes of our labels. All right. So when we said, where are we at here? Right here. We said call label 1 from label 0. From that context, right? And when we do that, these are magic tricks, right? This is the magic trick. Here's the inputs to that magic trick. And as part of that, there's a circuit built into our CPU. And that circuit's going to do some stuff. Now, we happen to know that among potentially, probably other things, it does at least one thing. What's the one thing that it does? throw something on the stack, right? So part of that magic trick, part of the wiring of that magic trick is something gets tossed on that stack. All right? So let's step over this line. So now we just popped CX. So pop is 5-8. And 5B is the destination, right? So 5B must be the magic trick associated with that register, right? I think MIPS, the register names, when you map them, it went from, I think what, like S1 was like a 0 and S2 was a 1, I think it went by 4 bytes, right? I think it was a 4. Yeah, whatever it was. But they had numeric equivalents, right? So we had our English name S0, S1, S2, and they had numeric equivalents. So this seems to be the numeric equivalent of, this is pop, and this is AX. Here's our next pop. Here's our add. And what's happening to our instruction pointer? We're currently at instruction 11 from base offset of 720, where our first instruction lives. So 720 plus 11 is there's our B. 720 offset B. That's where we're currently sitting. Jump past that. Now we're at instruction pointer D, base address 720, offset D. Couple of pushes, then we get to our return. Return bounces us back to there. That is offset 7 from our base address of 720. So if we roll back here, here's our original instruction starting at 7200. Here was one instruction. Here was our second instruction. Our third instruction took these three things. But the address space of those was offset 0 through 6. So the next available address space for this instruction was off the base address 720, 7 hops of size of instruction, right? Or size of part instruction. So since this is a 16-bit chip, size of would be 16. These are jumps.
That would be one instruction.
No, well, since instructions obviously have different sizes, right?
Yeah.
It would be one, the size of a single byte code. So we could even say it's size 8 if you want. I mean, it really depends on the processor's architecture. It's the unit of movement associated with a single index. So as our processors get larger and larger and larger and have more and more magic tricks, we need larger indexes to index all the magic tricks. Make some sense? So that 7 was an offset, not an instruction offset as we are viewing them, but an instruction offset at the binary level. What our assembly language code converted into an offset there. So if we were looking at the assembled version of this code here, it looks like this, right? So if we wanted to write this program even more cryptically, we would write our code, we would say 6A followed by, well, I mean, so this is in bytes, right? So this is the size of this is a byte in 8086. So that's what our size of is. But don't necessarily think of it like that because it's going to be larger in more modern spaces. So these guys are represented as 2 nibbles because it takes 4 bits to represent a hexadecimal digit. HexTet. HexTet is the actual name of it. We figured that out last night. So a digit equivalent in hexadecimal is a HexTet. Could be a quiz, but probably not. All right, so this is a HexTet, this is a HexTet, and it takes 8 bits to represent this HexTet. So that means the number of unique magic tricks that we can represent in the 8086 architecture is 256 unique magic tricks, right? If we chose to use all of them. This isn't necessarily dissimilar to how ASCII works, where we have ASCII is an 8-bit character set. So we have 0 to 255, so 256 unique characters could be represented in ASCII, but if you look at the ASCII character map, after we finish with the alphabet and our digits and some of our punctuation, we start using the other stuff as filler, right? We have like smiley faces, and we have like playing cards and stuff like that that we're just using to represent those things. So just because we have enough space for 256 unique magic tricks doesn't mean we necessarily use all of that. But keep in mind, it's not just magic tricks. Those 256 unique indexes, if you will, each mean something unique. Some of them relate to magic tricks. We've seen some of them relate to the numeric name of our registers, right? We call AX, but under the hood, that has a byte size descriptor. Make sense? All right, so this guy is the name of our magic trick. That's 7200, so this is our very first guy here, which is push 15. So we are saying, call this guy, and this is whether or not it's an on or off for electricity and what the inputs are. So this guy has one input. One input here is going to be a 15. No inputs to that guy. One input here is going to be a 21. No inputs. This guy, E8, which is call, has 2 inputs to that instruction. Under the hood instruction, this guy got assembled into something else, right? When we assembled it, it turned it into the magic trick code. So call has a magic trick, and then the 2 guys that are associated with that, the 2 inputs to that magic trick, are the current label, the current position, and where we're going, the destination label, for us to make a jump in the code. Okay? Starting to make some sense? When we look at the assembly code, we're looking at human offsets because we're looking at our code. These guys here represent offsets of the machine code. Understand the jump we had to make to see those 2 things? So the offsets are accurate. We were just counting human lines instead of machine lines.
We just got lucky the first time it was 3 that they had.
Well, I mean, it was
Like the next one.
random luck just because the first we had a 2, 2, and a 3. So no, actually for that version it was a just a 3. Yeah, because our very first call was the call AddNumbs. So it just happened to be a size 3 for our offset because that's the number of bytes. It was a 3-byte call in order for that guy to work. All right. So does that make sense? How our code segment base address here, so that's what this guy is, right? Base address of our code segment. Now, every single time we've run this, it pretty much looks like it's in the same thing because the emulator must be grabbing some memory and saying that's where it is. But we're not necessarily promised that the base address of our code segment is always in the same spot, right? In fact, if we start adding some variables, we might notice it changes. Okay, so where is the code segment of what's the base address of our code segment? It's whatever is in CS. And what is the offset from that where our next instruction lives? It's in IP, the instruction pointer, which is an offset of our code segment. And those 2 guys built together give us the full address of that next instruction. Make sense? Yay, nay. Okay. So we should consider ourselves lucky that we don't have to write code that looks like this. Wouldn't that suck? And you thought this sucked. Because we have a whole bunch of lines of code here that literally accomplishes almost nothing, right? Just adds a couple of things. Now, what's the downside? So kind of let's go back to what we were accomplishing now we understand the pointer. What's the downside of me using the stack in this way? So I'm utilizing my stack to store two values that I want to add together. So it's how I'm passing my parameters, right? So I'm utilizing the stack that way. Then I'm calling AddNumbs, and we know AddNumbs manipulates the stack. So as the programmer here, we have to be aware of that. And we did. So as soon as we got into our AddNumbs procedure, we went ahead and said, okay, well, let's go ahead and preserve that bounce back pointer inside of a local register. We could have also done this in a variable if we wanted to, but we need to preserve it because I'm about to look for some of my parameters on this stack, and there's an extra guy there that we had nothing to do with. Make sense? So we popped that off the stack, which actually physically removes it from the stack, and we stored it inside of CX. Then we started doing our mathy stuff. We grabbed our first parameter, grabbed our second parameter. Actually, we grabbed our second parameter, then we grabbed our first parameter. Then we added them together, giving us the result in AX. Then we pushed AX onto the stack, and then we put the stack back the way we found it by pushing CX back onto the top of the stack, which then allows the return command to work. Because what does the return command do? It changes our instruction pointer to base address of the code segment, CS, plus the offset that's in our instruction pointer. This guy got loaded back into the instruction pointer. Make sense? We had to preserve our instruction pointer because our instruction pointer needed to change as soon as we moved toward this other procedure. We only get one instruction pointer. And that instruction pointer is always pointing to an offset off the base address of our code segment where the very next instruction to be executed lives. Well, I have instructions I'm going back to. I don't have multiple instruction pointers. We can never have enough instruction pointers. We would need more than two potentially, right? If you have functions that call functions that call functions, or procedures that call procedures that call procedures. So that's where we utilize the stack. That's where the stack is not just utilized by us, but it's also utilized by the magic tricks. And we're going to throw this value on the stack and come back to it. So we have to be aware of that if we're going to use the stack. Now, what's the downside of using the stack as we've used it here? Besides that, yeah, I mean, obviously, yeah, we have to worry that we're going to break the stack. Right? So when we popped that value off and just relied on our, the 1C that we put back on there and just hope that's an instruction. It's like, well, it's not going to be the next instruction, but it might be a instruction. So all of a sudden you just jump to some random place in memory and just keep kicking, right? That's going to give you some weird experience. So, punchline here is that we at least need to be aware of manipulations to the stack. All right, so after that, assuming we're aware of that, we kind of know, if we need to preserve the state of the stack or something. What's the downside of using our stack for passing parameters like this?
If you want to continue to work with, so if we were doing more than just adding those two numbers, if we were going to continue to work with those two numbers, you would need to store them in a variable or something besides the stack. So why would you use the stack when you're going to have to use something else?
Well, you wouldn't need to. You could still keep working with the stack if you want.
But it would be just a pain to have to.
Why? The real answer I'm looking for.
Popping and pushing and popping and pushing it back on there, right?
And also the management of it, where, what's the advantage of a variable?
That variable is, you don't have to worry about something new being pushed on.
We have a name associated with a value, right? We don't have to worry about was the first parameter at the top of the stack and the second parameter was the second guy, or was it the other way around? We just throw them in a couple of variables and use those variables. Make sense? So variables have their advantage. What's the disadvantage of variables? So disadvantage of the stack is it's unnamed. Right? We have to juggle the position of all these things. Like, I'll just push a couple things on the stack, we'll pop them off the stack. Hopefully I don't forget what each thing meant. If I go back and look at it, if we're writing anything complex with what? After 6 lines of assembly code, it's complex, right? So if I'm doing anything complex whatsoever in assembly, that stack is going to start looking like gibberish pretty quick, all right? So we have to start remembering what each of those lines mean. So that's the disadvantage of the stack. It's an unnamed values. The advantage of the stack is it's fast, right? This is memory that lives on the CPU. It's not register fast. It's fast. Now, technically, you could implement in very early CPUs, you could have the stack live in main memory. But most of our modern CPUs will have a stack that lives on the CPU for fast access. Think of it for the very reason of like calling a procedure. We don't necessarily want a procedure call to be slowed down because we have to go to system RAM in order to call that procedure, right? System RAM is fast by human standards, but slow compared to a register. So we wouldn't want to be dissuaded from using procedures, modular programs, in order to write this stuff just because, oh, it's going to be too slow. So stacks are anonymous. Okay, we lose the ability to name our variables, but they're fast. The flip side is variables are slow, relatively speaking, but we have ability to name them. We can call it num1 and num2. Make sense? All right, so let's look at some variables here. So I have a guy up. All right, is this our... Yep. All right, so here are the various things we have in our this is the various types of values that we have in our 8086. So we have a data byte, a data word, this is a data double word, a data quad word, and a data 10 bytes. All right, so this gives us various sizes of things. And I think this is 8086 specific, yeah. So these are the guys that live in that architecture. In newer architectures, we start thinking about larger values, right? As memory got bigger and bigger and bigger, it makes sense that we might want to work with larger things. So we can actually store things in megabyte size stuff and things like that in newer Intel architectures. But these are our primitive types. If we're drawing a comparison to Java here, these would be our primitive type values in 8086 assembler. Okay? So if we only need something in a single byte, we would use a data byte. If we need something in 16 bits, a double byte, we use a word, and so on and so forth. All right, so let's look at a couple of these examples here. There's also some stuff in the data section you can do to manipulate things, but let's start off with a simple example. All right, so in our data section, I'm going to create couple of variables for our parameters. So param1, param2 will make both of those guys. We are loading them into, we seem to be doing our math inside of 16-bit registers, right? So how big do we want our values to be?
63,300. Those were
Yeah.
different.
Yeah, those aren't even related to
The 65,000 is the number you're looking for.
65,535, that's not the number I'm looking for. AX, what's the size of AX? Cat, dog, 16 bits. So your options. Let's just go with cat. I think the guy used to have cats. Go ahead. Okay, AX is a 16-bit register, right? Okay. What about AH and AL? 8 and 8, right? Those are the high and low of that 16-bit register. Now, when we look at our code here, we've been doing our we've been doing our math using AX, right? Which is a 16-bit register. So we're doing 16-bit addition. So if we're doing 16-bit addition, we want our parameters to live inside. I mean, it doesn't have to work this way. We can do addition with 8-bit registers if we want. But if we're staying consistent with what we're doing here, since we're doing math with 16-bit registers, our variables that we're going to choose to do math with now should be 16-bit variables, right? Okay, so which of these guys do I choose for my 16-bit variable? Is it a dB, a dW, a dd, a dq, or a dt? dW. So that's a word. And a word is a 2 byte. Okay? So 16 bits. All right, so this guy's going to be, we're going to say param1, DW. Now, what do you suspect is the difference between me saying 25 here and me putting a question mark? Yeah, it's not initialized. And is that okay for us? And we don't want to use it before we initialize it, but we don't really know what the value is going to be yet, right? So we'll go ahead back into our code. And this is inside of our data segment. All right, data segments where we define our variables. So in our data segment up here, we'll go ahead and create a label. We'll call this guy param1. And this guy's going to be a DW. And we'll start it off as nothing. Then we'll say param2. This guy will be a DW. We'll start that guy off as nothing. And then rather than pushing these guys onto the stack, we will move into param1, our 15. We will move into param2, our 21. Let's do this for right now. We're going to do move into AX. We'll call this guy answer. And we'll assume answer is 16 bits, so if we get an overflow, it won't fit, right? If we try to add two humongous 16-bit numbers, so here you get to use your thing. So if we try to add 65,535 plus anything, it's not going to fit inside of answer. So we might choose to make answer larger if we wanted to, but we get carry flags and stuff like that. So
if I set it to higher than that, would it set that, like how would it do would it be 0, 0, 0, 0, and it would
move won't let you do it. So if you try to move a value that's too big for its destination, it'll scream. But if it's the result of an add, that's when flags get set. Yeah, the arithmetic operators start setting flags, letting you know, look, I put as much in there as I could, but you have carry flags set, and if you're doing 32-bit math, it'll use AX and DX for overflows if you're using the registers for doing the math. So it's more of a trick thing, not something you need to worry about right now. All right, so we have three things here for our two parameters and then our answer. We'll make these all words, so 16 bits. So we went ahead and moved 15 into param1, 21 into param2. We call AddNumbs. We'll go ahead and move answer into AX after this is all done. We no longer need to pop the top of the stack to preserve it because we're not manipulating the stack now, right? We're keeping the values there, so we don't need to pop that. We don't need to pop AX or BX either. Now, we could say move into answer param1 and then add answer param2. This wouldn't break anything, just leave it. Don't need to do any pushing again because our solution is inside of answer. We'll go ahead and return. Save this, run this guy. Wrong parameters. So move answer, comma, param1. Well, let's go to our documentation over here, which we have set up, is it this guy? All right, and we want to get to our move command. So let's do well, I guess we're just going to have to jump down here because I figured it would help us jump pretty quickly, but it didn't. I did put a link to this up on Blackboard, right? Pretty sure. Because this guy's pretty helpful for us because it'll tell us what we're allowed to use for those guys, and we'll see what our limitation is here. All right, so here's our possible inputs for move. We can move memory into a register. We can move register into memory. We can move register into a register. We can move an immediate into memory. We can move an immediate into a register. Nowhere do we have the ability to move memory into memory, which is what we're trying to do here. That's why we got the error. So move doesn't work like that. So that means we have to go back. Fine. So first, we could move into AX, param 1. Then we could add AX, param 2. Then we can move into answer whatever's in AX, and then return. So this is move register memory, add register memory, move memory register. I think those were all on our, well, we didn't look at add, but for the moves, those were all on our list of allowable things. Now, why do you think we couldn't move memory to memory? Why do you suspect that's a limitation? What time are we done? 2 minutes ago? Oh, all right. Let me just answer it real quick. So, all right. So it's because memory lives somewhere else on the CPU. All right. So since memory lives somewhere else on the CPU, it takes time to get there. So we'd have to retrieve it, come back, and then go back to store it. All right. So I'll put your homework assignment up, but your homework assignment is to write the Hello World program, but your output, the way you output to the screen, should be done through a procedure. So you're going to write a procedure for writing something to the screen using local variables. And I'll give you this code as a starting point. And then the Hello World is also a starting point online. So modularizing the Hello World program that we've seen.